solid-state drive. I'm Sang-won from Sungakyunkwan University, Korea. After a brief introduction, I'll talk about the share interface, which is a new abstraction for flash memory SSD. And then Sundar will talk about the ForestDB optimization for modern file system layers. Okay, as you may know, we are witnessing the advent of all-flash storage era. Right? However, modern system software have been developed for the last several decades to assuming the hard disk as its main storage devices, right? So that reason, if we run system software stack on top of flash storage, the performance might be suboptimal, right? Meanwhile, the ForestDB is the next generation key-values engine for Couchbase, and it is optimized for flash memory storage, right? However, it follows the design principle of its predecessor, CouchStore, in that it uses the copy-on-write approach, and the costly compaction operation is not inevitable. In ForestDB. So, in order to further optimize the ForestDB on top of flash storage, we investigated the opportunity provided by flash storage and file system. And the first result is a share interface in flash memory SSD, and the second one is how to leverage modern cow-based file systems. Okay, let me move to the share interface. Before explaining about the share interface, let me explain some characteristics of flash storage. Okay, as you may know, the flash memory chip do not allow overwrite, right? So in order to overwrite some data, you need to erase the flash memory blocks, right? So for that reason, the flash storage device need to maintain another address mapping layer inside the flash storage, and the address mapping is managed by FTL layer, which is an firmware controller module inside the flash storage device. And the modern flash storage has limited erase time, so the flash storage has a limited lifespan as storage devices. And lastly, the write time in flash storage is very proportional to the amount of data to be written to the storage, right? But unlikely in hard disk, the write performance is dominated by the number of disk arm movement, mechanical disk arm movement. So these three are the mostly closely related characteristics of flash storage to our techniques. Please remember that. So then let me explain the copy-on-write in ForestDB. So when updating document in ForestDB, instead of overwriting its original version, we need to write the new version at the other locations. And the location of other versions are changed, so we need to propagately change the index tree node, right? So if we update one document, we need to update the several pages, right? We call this situation as tree rendering. So in updating a document, we need to write several pages at the end of the files. We call this situation as tree rendering, and it causes a severe write amplification problem in ForestDB. The reason why ForestDB and its predecessor CouchStore take a copy-on-write are twofold. One is about write atomicity, and the second reason is multi-version compaction control. So as you know, the modern OS operating system and the storage system do not support the atomic write property. So one way to easily overcome that problem is to take a copy-on-write approach. And as it is well known that the copy-on-write is very good for multi-version compaction control. And this approach is very, very reasonable in hard disk era. And I believe that this sequential write pattern is very, very good for flash storage system too. So that is the reason why ForestDB is very, very competitive against the other vendors. However, the copy-on-write approach has two problems. The first one is, as I said, the tree rendering and its implied light implication can degrade the performance of ForestDB. And because it writes many data, so it can shorten the lifetime of flash storage. That is the problem we want to solve in this work. So then what is the opportunity provided by flash storage? So as I explained, inside flash storage, there is a page mapping table. Because the flash storage do not allow in-place update, so we need to maintain the logical address from the host system and the physical address in flash storage chips, right? So we need to maintain address mapping table, right? But the current modern flash storage try to mimic the hard disk interface. They only support read and write interface, right? But I think there is an opportunity to solve our problems. So with that background, we propose share interface. By share interface, the user can change the address mapping explicitly from the host side, right? So let us assume that we are updating document D2, and its D2 version is written in other location, right? After writing the D2 version in other location, by calling share interface with the D2 logical address and the D2 prime's logical address, then the D2 can access the physical version of D2 prime, right? So we do not change the index tree node, such as C and A. So we can avoid the problem of tree rendering, and we can reduce the light amplification significantly. So that is the key idea of shared interface. And again, it allows, it provides new address remapping to the users with explicit interfaces. So the share is very, very good in optimizing the normal time document update operations. And the other advantage of our share interface is in compaction operation of ForestDB, right? So the original compaction operation is reading the old valid document from the old files and to write the valid document to new files, right? But with the share interface, we just create the new file and we allocate some spaces. Then by calling the share interface, and the new file can share the old files without writing the document itself. So we can significantly reduce the right amount of time while processing the compaction operations. Right? So we implemented the share command by extending Perl module in OpenSSD board. And the OpenSSD board is a real platform which is commercialized by OCC technology. Even though it is somewhat older, but it's a very realistic OpenSSD. And it is very, very critical to implement the share command in an atomic way because we should consider the system power off and system failures. So we made our share command inside flash storage very, very atomic and recoverable. So let me explain the performance of the effect of our share interface on normal time performance. So we use the YCSB's write-intensive workload F. And as we see, the OPS of our share can outperform that of the original ForestDB by 2 times or up to 3.5 times. And as you see on the right side, the amount of data to return to storage can be reduced by 1/8 of the original ForestDB. Right? And one thing I'd like to say is the write amount is reduced means that the compaction operation is, the calling of a compaction operation is delayed. So if we apply our technique, the compaction process is less frequently cold. And what is the impact of shared interface on ForestDB compaction? So the elapsed time of one compaction was reduced by almost up to 2.5 times, and the amount of data to be written while compaction was reduced almost by up to 1 magnitude of 1 by 10 times. Right? But one thing that, as Sundar will talk, our OpenSSD platform did not support the asynchronous read operation. So we could not apply that technique. But if other SSD can provide that functionality, then our compaction time will be reduced more significantly. I expect we can improve 10 times performance improvement if the SSD can support that functionality. Okay. So this is what I like to say, and Sundar will take up the last of the presentation. Thank you.
Good afternoon. About how excuse me. Oh, hello. Am I audible? Yeah. Oh, thank you. So in this section, I'll be talking about the ForestDB optimizations that tactfully utilize some of the existing features in the file system layer and the OS layers to achieve similar results to what Professor Lee just presented with the share API, except that these use features that are already tried and tested and in current file systems. So to start off, I'll be explaining the catch-22, which is basically a fundamental problem that exists in the append-only world that use MVCC. This fundamental problem is something that exists in almost all typical deployments of the append-only KV store models that we see, including ForestDB. And then I'll be talking about how B-tree file system or Btrfs helps us address this catch-22 problem. And then I'll also be covering the performance results using the libaio that Professor Lee just mentioned to optimize this even further. So to begin with, having said that there is a fundamental problem, I'm kind of obliged to explain why we would even pick the append-only KV store model, because it's great. It offers several features, and it's very popular in the industry for reasons like you can create multiple stable point-in-time snapshots, which means when your writes are coming in, it's not affected by the readers because they read a consistent point-in-time snapshot. You can have complete isolation of the readers and writers so they don't block each other, so they can run at optimal speeds. You can recover easily because you can roll back to a past stable point-in-time snapshot trivially without having to do complex manipulations. And finally, it's SSD friendly. SSDs don't like data written to the same location repeatedly because they have limited write cycles and stuff like that. So what they do is they have this flash translation layer that works underneath that basically remaps your writes to new locations. Now, if you are not writing to the same location and you're doing append-only, you're actually increasing the performance because you have fewer flash translations that simply happen. So for those reasons, append-only KV stores are great. But now where the problem lies, to just explain, let's look at a zoomed out view of a disk. We have a disk here, and then we create a file system on it. Let's call it file.fdb.0, and the writer continues to append data onto this file. Now that's great. If the data were to be updated, all that we do is that we just write a new copy of it, and the old snapshot continues to exist. So the readers can now access the stable snapshot while the writer is still appending. So the readers and writers can run unblocked. However, there is this caveat: the disk can quickly fill up with space, and you need to do garbage collection. That is compactions. So compactions currently work as follows: we create a new file, file.fdb.1. We read all the valid data from the old file, move it into the new file, and then delete the old file, removing the stale and valid blocks. And that's how compaction is done today because it's simple and it works and it's performant. But however, there is a fundamental problem. Now, what if this big green, the bright green space is bigger than this white space that you see here? You cannot really do compact because what happens is you cannot free up space. And that is where we hit this fundamental problem, which is the catch-22. Your disk is full, you want to free up space, but you don't have free space to free up space. So That's a fundamental problem, and you'll typically find this in the fine print of a lot of the append-only KV store models. The rule that's hidden and not typically exposed is that your size of active data cannot exceed the free space available on disk. Now, this is kind of counterintuitive, because when you tell a customer that you need to have a disk, but we cannot use more than half of it with useful data, that's kind of like, oh, they generally assume it's for redundancy. But then you tell them that, oh, it's not for redundancy, it's really the way we do compactions. To free up space, you cannot fill up more than half your disk. That's kind of confusing, and then they ask these questions, and you have support and all that stuff. So there are multiple ways to solve this. One of the ways to solve this is punching holes inside your file to free up space. The other one is a more generic solution that we picked, which is using the Btrfs file system. Now, if I may quickly request, how many of you, for a quick show of hands, have heard of Btrfs file system? Okay, that's quite a few. And how many of you have deployed Btrfs file system by any chance? Okay, one. We do have, that's a non-zero number. Non-zero number is good. So to give you a quick introduction on Btrfs file system, Btrfs file system is primarily a copy-on-write file system, which is considered as the next generation file system for Linux. There's an interesting history behind it. When the development began in Oracle in 2007, there were some patent wars with NetApp and the Sun Microsystems and ZFS, because of which we have, the end of the day story is that we have a copy-on-write implementation that is hassle-free in terms of patents and lawsuits and all that stuff that you don't want to really get into. And it's enjoying a lot of industry support from several big names like Facebook, Fujitsu, Fusion.io, Intel, Netgear. It's deployed in production in companies like Facebook, Rockstore, which is a storage, Netgear, TripAdvisor. So all of those have deployed Btrfs file system in production. And even the creator of ext4 actually believes that Btrfs file system is the direction in which Linux file systems will be going forward. Because ext3 essentially is like a decade-old file system where we apply new patches like write-ahead logs and stuff like that to overcome some of the limitations that are there. But sooner or later, they believe that it will hit roadblocks, and Btrfs file system is the direction it's going forward. It's available as an option on all Linux file systems. SUSE file system uses it as the default engine. It comes with a host of features that are very friendly to modern data centers. Stuff like you can create 16 XB bytes of file, more than what an average data center guy would typically want on a single machine, but nevertheless, it's still there. It's self-healing because it's copy on write. You can do online defragmentation, you can grow, you can shrink. I won't be covering all the this because this list is of course a short one. Out of all these illustrious features, we shall be using just one, which is primarily file cloning. That is what is going to help us solve the catch-22 that I just explained. And to explain what this file cloning feature of Btrfs is, let's have a quick look at what the way Btrfs file system represents disk blocks and extents. So what we are looking at here is, let's say, a file P, which is a gross simplification because Btrfs uses extent trees and stuff like that. But for simplification, let's say this is a file P. You see those numbers next to those blocks, those nodes, which are basically reference counts on the number of accesses that are there. This will work typically if you have a representation that is a directed acyclic graph, which fortunately most file systems are. So with this, you can do something like a copy file range. So you can create a new file that simply refers to the blocks of the old file. In Btrfs, this would simply require you to increment those numbers on the intermediate nodes that are shared. The nodes, the leaf nodes are actually left intact. So this lets you implement a trivial way of doing cloning or copy file range. With this, you can have a new file that shares the physical blocks of the old file, and it itself can grow in this way. As you can see, it grows into, you can have new blocks, and you can have some of those new blocks still shared across with the old file. This is the primary feature that Btrfs provides by default. This is one of the things that were there in it from the start, from its inception. And then deleting a file is simply, let's say on compaction to delete file, simply decrementing the ref counts on all those nodes, and freeing up space is simply removing all those extents that have a file that have the reference count of 0. At this point, actually, I should mention that Btrfs is very SSD friendly in the sense, right at the point when you mount, right, it would print out this command saying that it has detected a non-rotating disk and it has already optimized it for the SSD. It offers features like FS trim and trim or discard, where you can remove out blocks out of your SSD that are no longer valid, which is very good if you can implement things that move across the erase blocks of certain SSDs and stuff like that. It lets you do those kind of things. Now, with this feature, we can address the catch-22 that I just mentioned. That is the fundamental problem with space. When we want to compact this file where you don't have enough free space on disk, you simply request Btrfs file system to clone all those valid blocks that are there in the old file and create a new file. So, we create this file.fdb.1, simply copying over all the valid blocks from the old files. Now, the old file blocks on the disk stay intact. We only create the metadata that with the new reference counts. So, as a result, compaction can succeed even when the size of active data is larger than the free space available. And then all that you need to do is simply delete the old file, which only removes the stale data. The active data blocks stay intact. So, in this way you can avoid the fundamental problem with disk space. Now, naturally this solution has been tested with ForestDB, and I will be presenting some of the performance results. Now, a thing to mention here is that for the performance results, right, what we did is that we used the stock version that came with Ubuntu. We installed Ubuntu and we installed the stock version of the Btrfs file system that came with it. Btrfs is actually at version 4.2 as of May 2015. However, we purposely did not patch the kernel because there are actually some companies out there that have done stuff like this. They want to optimize SSDs by providing a custom patched kernel, which kind of gets a lot of friction from the industry because they don't want to know if they can install custom kernels and patched kernels, how much they can trust. There's all those kind of issues. So, we wanted to leverage the trust, the chain of trust that's already established. If you trust Ubuntu, Ubuntu trusts this version of Btrfs, well, you're already there. Now, it's like digital signatures. So, this is the configuration that we used, the 4-node, 4-core with 20 GB SSD and 8 GB of DRAM. And the first set of results that we see is actually using the page cache. This is with the page cache, that the OS page cache still intact. I should mention that these are not the super impressive results that will come up later, but we still did the test, and I'm still presenting it anyway because we believe that this is the kind of deployment that you might see in a typical scenario. That is, you might still have the OS page cache freed up for running where a large portion of your data fits into memory. So, even in this kind of scenario, we see that with the block caching effects and stuff like that, we see as much as 2x faster performance as the value sizes increase from 512 bytes to 1K to 2K. We see that we see greater speed ups in the time that it takes to compact a file when we use the cloning, the Btrfs with cloning versus with the vanilla original approach. We did another test where we increased the size of we decreased the buffer cache so that entire data fits inside the buffer cache itself. In this case, what happens is the normal compaction itself is fast. As a result, you see gains, but those gains are varied because of the caching effects. Nevertheless, in all these cases, you still see 1.5 to 4x speed up in the compaction times. That is, you have to wait that much less for the file to compact. And throughout, all of these result in half the amount of write amplification because you do not need to copy the valid blocks from the old file to the new file. The last set of results with the OS page cache is with heavy DGM, that is where the data exceeds the buffer cache that ForestDB itself natively has, and we see expected gains. We see 512 bytes value sizes. We see a little less gain as the value size increases. We see more gains because in the implementation of the cloning, we simply don't copy or we don't write the valid data from the old file to the new file. So, we save on that much time and your gains will speed up with the value size. However, in our current implementation, we still need to read the metadata from the old file, and when we hit scenarios that are heavy DGM, that is your data is much greater than memory, it does not fit into the physical RAM, that is where you become IO bound. Now, when you become IO bound, your gains typically fall because what is happening is much of the time is spent inside the reads. So, we wanted to optimize this area by adding the libaio. So for those familiar with libaio, it's basically the Linux asynchronous library. It's actually extremely recommended for high performance SSD, because modern SSDs actually have several channels. Like you'll most typically see at least 8 channels, and libaio lets you submit asynchronous requests with queue depths of up to 64 or larger, and then have them all read simultaneously. We have seen some hardware configurations where there are as many as 6,000 I/O pathways to your disk. So that's the direction the industry is going. In fact, right after this, there is a talk from the Intel folks who will be presenting some interesting benchmarks by running ForestDB on the next generation Intel NVMe. I would highly recommend you to check that out. But here we tried the same ForestDB with the libaio library, because it's well suited for this particular task of compaction. Because in compaction, we need to read all those blocks from the old file. And when we use libaio, here are the results that we see, which is in the DGM scenario. That is where we are I/O bound. With 512 bytes, we see as much as 4x faster compaction times. As the value size grows up to 1 kilobyte, we see 7 times improvement in the time it takes to compact a file. And when the value size grows up all the way up to 2K, which is actually not uncommon for NoSQL land, where you can have JSON or blobs that go all the way up to 2K, you see 13x faster. And this typically linearly increases as your value size grows. You have to spend less time compacting, because you're simply sharing all the valid blocks from the old file. So to quickly summarize, the Btrfs with libaio efficiently uses the disk space. It avoids this problem of the catch-22, which exists in the append-only KV store models. It reduces the write amplification simply by 2 times, because you don't need to write all the valid user data over to the new file. You can have over 13x faster compaction speeds. And most importantly, this is a generic solution that applies to not just SSDs, but you can also apply to spinning disks to speed up your compaction times. So there is actually plenty of work that can be done that we have slated for in the future releases or the future versions of in ForestDB. Primarily, we found several areas within the Btrfs clone feature itself that can be optimized. We are working actively with the Btrfs community to see if we can include some of this into the mainstream Linux Btrfs the branches. There is of course a process in which we submit kernel patches, and we hope to get that done so that we can optimize this area of compactions even further. And then we also want to see if we can improve our own ForestDB's metadata store, so that we can skip the entire reading portion of the ForestDB, so that we can completely eliminate I/O in the compaction phase, which needs to be. And lastly, for those who might still be uncomfortable deploying B-tree file system and moving to the next generation file system, we also plan to implement this kind of a feature, this kind of share physical block feature into ext4 itself, so that there is nothing further, there's nothing new that you'll have to deploy or install, and you can just run ForestDB out of the box and it runs fast. So to quickly summarize, as Professor Lee presented, we have the share interface that speeds up compactions by 3 times with 10 times lower amplification. However, this requires synergistic cooperation between the APIs and the firmware or the open SSD modules that we saw. Then we saw the Btrfs clone feature, which speeds up compactions by 2 times with 2 times lower write amplification. And when you add in the Linux asynchronous library into it, you can have speed ups to up to 13x with half the write amplification that you typically see in the normal SSD, in the normal vanilla version. So with this, we are hoping to have a lot of questions from you, and we have a lot of time. Both me and Professor Lee are here. So in case you'd like to ask us any questions about ForestDB or about these optimizations, please feel free to ask. But before that, I'd just like to mention one thing, is that at 3:45, we'll have a talk by the Intel folks who have run a bunch of benchmarks, and Chi here, who have run a bunch of benchmarks running ForestDB on the next generation Intel SSD. There's also going to be some interesting prizes that will be given away, so please hang around if you're there. So please, yes.
So do you intend ForestDB to be used only for indexes, or do you use that for normal files as well? I mean, what's the intention?
So right now, ForestDB, oh, sorry. So the question is ForestDB going to be used only for indexes, or what's the slated use for ForestDB? To answer that, right now currently in this, the version that is available as of today, it's used, ForestDB is actively in use in indexes, in mobile, Couchbase Lite. It's also used in CBFT, and in the future, in the very near future, we are going to also replace it as the default key the engine for the key values use case, which is our Couchbase server, Memcached, the primary product. And we'll see, eventually we want to have it as the unified storage engine that's going to be the way to access data of the disk. So it's slated for use everywhere within Couchbase server. Yes. I'll answer that. So the question is that with very small value sizes, we seem to see lower gains, or we seem to see a problem with Btrfs clone feature. Well, the answer is actually very simple. What happens is the gains that you see by using the Btrfs clone feature is directly dependent on the amount of data you need to move. So in our current implementation, like I mentioned, we still need to read the key and meta from the old file as we move it on to the new file. So what happens is when your value sizes are small, that cost is kind of amortized in the read phase. So when you amortize the cost in the read phase, your gains are shorter. As your value sizes grow, you see bigger gains, because the value portion of the key of the data is not touched inside the cloning. So as a result, it appears that smaller value sizes seems to have a problem, but this actually not a problem. It's just that the gains from the smaller value sizes are not as significant as the larger value sizes. So, any other question? Yes, please.
I don't know databases, but I have this question about the metadata.
Huh?
You said you are an append-only
Yes.
database. Does metadata update itself dynamically?
Does metadata update itself dynamically?
Yes.
Can you please clarify? I mean,
Well, if you're appending,
uh-huh.
so your metadata must be dynamically updating itself and become available for reads to other entities, right?
Right.
And so one of the problems in databases that happens is lack of elasticity, dynamic real-time elasticity. Something that other databases, for instance, I'm sure you have heard of Ceph. They talk about elastically updating metadata.
Right. Okay. So that's an interesting question about elastically updating metadata. So Chiang has actually covered portions of it inside the in his talk. We are going to have a support for it by way of supporting appends and prepends. Now, in order to grow the metadata or the data section, what you might have to do is append. We are still append only, right? So if let's say you have metadata that grows over time, what happens is you need to write the new delta or the diffs along with the whole file. So we are going to have in our future work a way to optimize this by supporting appends and prepends. So what happens is that let's say if your metadata grows by a small fraction, whereas the large fraction of your metadata is still valid. In our append-only model, instead of copying over this new huge chunk, what we would do is we would simply just write out the diff portion, the portion that has changed, that has mutated over time, and have our larger metadata, our indexing to suitably account for it, so that we optimize the way in which the data grows incrementally. So please let me know if I answered the question.
I have another question, which is also a little bit, and I seek your forgiveness. When you have the key values, is this the hash version, the hash?
Oh, so there are actually multiple layers in which there's caching that's happening. The first layer of the caching is happening independent of us, which is the OS page cache. If you have some free memory, most likely Linux, most versions of Linux will have large portions of that memory available for the disk page cache, which basically mirrors the disk blocks. In addition to this, we also, ForestDB also has something called as the buffer cache, which is its internal cache, which is smarter than the OS page cache in the sense it knows which blocks are more important and which blocks are have lesser priority. So that's the second layer of caching. In addition to this, there's also a wall section inside ForestDB where also the keys and the fast access data is also cached, which is essentially a hash table with distributed logs. So there are actually multiple layers in which data can be cached, so to speak. Any other questions for me or Professor Lee? Okay, thank you.